So, welcome to this week's Origins Colloquium. It's a great pleasure to introduce Ichiro Komatsu, who is the managing director at Max Planck Institute for Astrophysics in Garching near Munich. Ichiro received his PhD from Tohoku University in 2001. He was then a WMAP, a postdoctoral fellow at Princeton, where I first encountered Ichiro from 2001 for a few years there. Then he became a professor at University of Texas at Austin for about 10 years, and in 2012 moved to be a director at Max Planck. So he has made many fundamental contributions to our understanding of cosmology, both through his participation in the WMAP team in the early years, and then, as we'll hear today, about his more recent work. And he's won numerous awards, including the Nishina Memorial Prize, which is a prestigious physics award in Japan. So welcome, Ichiro. It's a great pleasure to hear about your work.
Thank you very much. Thank you for the invitation. Thank you all for coming. So I'd like to tell you about parity violation in cosmology, which is probably the topic that's not familiar to many of you. So I try my best to convince you that this is an interesting topic. So let's say the overall theme is we want to find new physics in cosmology because we know that the current cosmological data require new physics, such as dark matter, dark energy. And for example, we have CDM, and each symbol like CDM is new physics. And for example, it can be W, warm dark matter, wavy dark matter, fuzzy dark matter. It may not be dark, could be black holes, right? May not be even matter, so to speak. And lambda can be not the cosmological constant, but dynamical scalar field. It could be modification of gravity instead of energy. Could be related to quantum cosmology. Lots of ideas, but sometimes we feel that we may be a bit stuck. We need more hints from observational data. And we realized that we completely overlooked one thing, which is parity violation. So this is, of course, not new in particle physics, but it's quite new in cosmology. So that's what I want to tell you. But really, the main scientific motivation is to find new physics and make progress in our understanding of dark side of the universe. So I wrote a review article on this topic, published in Nature Reviews Physics a couple of years ago. So keyword is CMB, so cosmic microwave background, polarization, quite standard in cosmology, but what's new in this article is this third component, parity symmetry. So it's available both in published version and archive, so I welcome you to take a look at it. So let's talk about parity. Parity is inversion of all spatial coordinates, not just X, not just Y, not just Z. You flip signs of all of three coordinates. And parity symmetry states that the laws of physics are invariant under inversion of all spatial coordinates. Therefore, violation of parity symmetry is the laws of physics are not invariant under inversion of all spatial coordinates. But this can be a little bit confusing because I think many of us learned in physics class that coordinates are not important. Physics exists regardless of how humans chart space-time. Who cares about coordinates, right? It's just a convenient mathematical tool. Physics does not depend on it, and that's correct. But another thing we learned was that coordinate transformation can be quite useful sometimes. So let's say you chart your universe in one coordinate and watch how things move. Then you switch the coordinate and then watch the same phenomenon in different coordinates. And then you compare how things appear differently. And that often gives you deeper physical insight of what's going on. So for example, Amy Noether, a German physicist, she proved Noether theorem that if your physical system is invariant under spatial translation. So that means there's no special location in space. It's homogeneity. This implies, as she showed, the conservation of total momentum. That's very deep, you see? So coordinates are not important, but you show that your physical systems are invariant under spatial translation, that's coordinate transformation, then momentum is conserved. That's a deep connection between conservation laws and the symmetry in space-time. Similarly, if you show that your physical system is invariant under spatial rotation, then angular momentum is conserved. So basically, generalized version of Nader's theorem is that if you have symmetry under continuous coordinate transformation, then there's a corresponding charge, which is Nader's charge, which is conserved. So that's a very, very deep insight. Parity is a discrete transformation. So it doesn't have conserved charge. But the question is, when you observe a certain phenomenon in nature, do we also observe its mirror image with equal probability? Now here, mirror, we have to be careful because we really have to flip all three coordinates, not just one. But just for the sake of simplicity, let me just show you some example where we only flip one coordinate, okay? So I guess colloquium is attended by both Europeans and the United States and other places in the world. I guess if you are in the US, you know what this is. If you're in Europe, you don't know what that is, that's fine. So in Munich, we play softball, the softball / baseball every Sunday. And then basically pitcher throws a ball, I hit, okay? So that's the rule.
That's a good hit.
Now, and now I flip coordinate, okay? One coordinate. Then I play this again. And question is, can you tell whether this is mirrored image or original image? So for example, if you only look at the trajectory of the ball, then it's same parabola in both coordinates, which means gravity only cannot tell you which frame you are in. And if you look at carefully, mirrored image, everybody is actually left-handed, lefty, right? Because if you have the glove on the right hand, that means you throw by your left hand, so you're lefty. And here, the way I'm hitting, that's also I'm a left-handed hitter. And I guess it's a bit odd because we know that humans, for some reason that we don't know, they're dominated by right-handed people. So it's odd that they're all lefties, but maybe this is possible, right? So that alone may not be enough to tell you that this image cannot occur in nature. What distinguishes between the original image and this one is the handedness of the runner. So if I hit and I run in this way, or I run to the right, mirror the image, I run to the left. This never happens in the laws of softball or baseball. So there's a definitive handedness in the rule book of softball. So if you knew the rule book, then you immediately know that this image is a fake. This image cannot occur in nature with equal probability. No matter how many games you play, this will never happen, okay? So this clearly shows that baseball violates parity. And I'm not so familiar with football or volleyball, basketballs, but from the limited knowledge I have, I think I'll be able to tell the difference whether I see the mirror image or original image for basketball, volleyballs, tennis, right? So, but baseball is clearly violating parity. So that's basically what we're talking about, okay? So parity transformation is not the same as rotation. Rotation is continuous, and its a determinant is +1. But parity is a discrete transformation, determinant is -1. So clearly it's not the same. And you can convince yourself, okay, it's an important point. So let's say you have right-handed coordinate system. Try to do parity. What you do is your right hand only give you three-dimensional rotation, never the parity. So if you wanted to do parity transformation, you really have to go to the left hand. Okay? You have to go to the left hand. Then you rotate your left hand about the z-axis by 180 degrees. So first, go to left hand and 180 degrees rotation around an axis. That's parity. Then you have all spatial coordinates flipped. It is essential that you have to go to the left hand. So that's why we're talking about distinguishing between left and right. That's the essence of the parity. So let's talk about vector. That's momentum. As promised, momentum exists no matter how we chart the universe. Momentum is momentum. But components of the momentum require coordinates. So I have this coordinate E hat. Then I write components along x-axis, y-axis, z-axis. These components depend on coordinates. I go to another coordinate, E hat prime, and I have different components, p primes. But I know because it's parity, change the sign of ex, ey, ez out. Then I know that this has to be equal to the original one because physics doesn't care about the coordinate system. So this immediately tells you that components of a vector change sign under parity transformation. But if you have angular momentum, pseudo vector, it's r cross p, and both r and p are vectors. Both change sign. So product not change sign. So components of angular momentum will not change sign under parity. So this is different from vector. It's a pseudo vector or an axial vector. Then how to prove parity in the experiment? It's easy. You form pseudo scalar. Okay. So let's say you have experiments, particles A and B. You measure linear momentum of particle A, then you measure angular momentum of particle B. Then you take a dot product. That dot product changes sign under parity, so it's pseudo scalar. Then you repeat this measurement over and over and over again. Parity is conserved. This product can be negative or positive. This negative and positive must occur with equal probability. So if you average them, it must be zero within the measurement uncertainty. If it is not zero, then that's a violation of parity symmetry. It's easy, right? And that's exactly what was done to discover parity violation in nuclear interaction in 1957. So Lee and Yang in 1956 wrote a paper saying maybe, they couldn't find experimental evidence for parity conservation in weak interaction. So they suggested some experimental setup. So Yang and Lee were theorists, but they had some idea about how to do this experimentally. Then Wu saw the paper, and then she decided to do it in experiment. So she's an experimentalist. What she did, following the suggestion of Lee and Yang, is you have cobalt 60, and there's a nuclear spin. That's pseudo vector. Using a magnetic field, you align nuclear spin in certain directions. So you know where J is pointing at. Then due to beta decay, electrons are coming out of cobalt 60. So you measure linear momentum of an electron. Then you have both vector and pseudo vector. You take a dot product, then you repeat these measurements. If parity is conserved, the dot product should be negative or positive with equal probability. Average should be 0. Found that it is not 0, and with many, many sigma. So there you go. She discovered parity violation in nuclear interaction. So it's a power of pseudo-scalar. It's an unambiguous test of parity symmetry. What did people think? So when Li and Yang wrote theoretical paper on parity violation, beta decay, Wolfgang Pauli, Austrian physicist, who is known to be super critical of others' work, he said, ich glaube aber nicht, dass der Herrgott ein schwacher Linkshänder ist. So basically, he didn't believe what Li and Yang was saying. It's nonsense. So basically, that's what he said. Then when Wu's discovery was announced in the physics community, he was like, exciting, but how sure are we, right? Skeptical. I mean, it's a healthy skepticism. No one believed it because it was completely shocking thing. So everybody, just out of prejudice, right? Not based on experiments, but just prejudice, they just thought, they took it for granted that parity has to be a fundamental symmetry of physics, all physics. But it was discovered that weak interaction violates parity. So this really is very educational. Don't take it for granted, right? Anything until it's experimentally. So basically, exactly that. So I ask, does the universe distinguish between left and right? And most people say, yes, of course. That can be true, really, right? It can be completely right, but I want to test it before I conclude that parity is conserved in the universe. That's all I'm doing. Okay. So let's use cosmic microwave background. So let's say you have a sky, you have galaxy, we are in the galaxy, then we observe sky from inside of our galaxy. So when you do full sky projection in galactic coordinates, then you have this galactic plane in the middle. Then we go to the longer wavelengths, so that's optical. Then we go to longer wavelengths, near infrared, far infrared, some millimeter, and microwave. Sky is full of 2.7 Kelvin black bodies radiation. But if you improve the sensitivity of your detector by a factor of 100,000, then you start seeing ripples, fluctuations, as well as galaxy. Yeah, you never forget that. You have a galaxy here. But the higher galactic latitude, you have the cosmic microwave background. Now, where do they come from? If you have the light that was emitted here in this location, they're already gone from us. So clearly that's not the light we are seeing. So let's say Big Bang, entire space was lit up. Then there was a light coming from one light year away. That light came in 1 year and then gone. So that's not the light we are seeing. The light that we are seeing was emitted 14 billion years ago. Like very, very far away. So far away that it took them 14 billion years to reach us. That's the cosmic microwave background. These photons traveled like crazy, right? Crazy time, crazy distance. Here we go. So that's a picture of the universe way long time ago. Okay, so it's the beginning of the universe. And we're talking about polarization. So each sky location, so that's our object. Okay, we need a pseudoscalar. How do we do that? So you saw the pattern of CMB polarization. It has directions. Because it has directions, you can decompose them into parity eigenstates called E mode and B mode polarization. E mode, B modes are parity eigenstate with opposite parity. So the product, B correlation, is a pseudoscalar. Now you can have, it's totally fine if you have this pseudoscalar in each sky location that's negative or positive, okay? But if you average them over the full sky and it is not 0, that's the parity violation. You can have EB correlation in each location, up and down, positive and negative. If the full sky average is 0, then it's not parity violation. So you decompose into Parity eigenstate. So basically, you have to go to Fourier space. Is a Fourier vector, and use ask with respect to the Fourier vector, the polarization direction parallel to or perpendicular to the Fourier vector or 45-degree tilted. And it is clear that these two modes have opposite parity. So the product is a pseudoscalar. You can also have square of each, like E mode square, B mode square, or you can also have temperature E mode cross correlation. All of these are scalar, not pseudoscalar. So these are not sensitive to parity violation, and they have been measured very precisely. This is called power spectrum. And so that's basically a squared coefficient of the Fourier components. But other combinations, such as temperature B mode cross correlation or EV cross correlation, are pseudoscalars, and they are sensitive to parity violation. So let me explain the power spectrum. So let's say I start with the sky map. Then I decompose them into Fourier components. Because it's a sphere, it's spherical harmonics decomposition rather than Fourier decomposition. Then if you go to the leftmost, so longest wavelengths, shortest wave number, smallest wave number, longest wavelengths, then that wavelength is as big as the sky. If you go to the right, you start seeing shorter wavelengths perturbations. Then, you shorter wavelengths, and by the time you're done decomposing, you might want to put them all back. Then, of course, you recover the original image. Like this. So nothing but spherical harmonics decomposition, okay? Then that's the results. So as we go to the right, it's shorter wavelengths, left, longer wavelengths. Then you have temperature power spectrum, E mode polarization power spectrum, B mode polarization power spectrum. They are measured beautifully. All of these are scalars. Don't tell you anything about parity. Look at EV correlation. Here's the EV correlation of WMAP and Planck satellite missions. So WMAP is NASA, Planck is ESA space missions specialized on CMB measurements. So that's EV power spectrum, chi-square with respect to null. So all I do is to take each data point and divide by the error bar. I square them, sum over L. There are 72 data points here. Chi-square is 125 for 72 degrees of freedom. It's a terrible fit. So it's not consistent with null. I mask the sky a little bit, right? This to avoid a very strong galactic emission. But it could be that we have some leakage of the galactic emission that's doing this. So let me remove more sky, mask more galaxy, signal stays the same. So it's not due to our galaxy, okay? That's very clear. So what is it? So let's try to interpret it, okay? Said this light came long time ago. It came from very far away, long time ago. As photons propagate, we typically think, okay, there's a lossless scattering of photons by electrons 14 billion years ago. This generates polarization because of Thomson scattering. Then we normally assume that direction of electric fields, say polarization, stays the same over 14 billion years ago. Doesn't have to be like that. It could rotate, okay? So over 14 billion years, you can have rotation of plane of linear polarization. Why not? If you have that, then because either you rotating right or left, right? Between left and right. So that's a parity violation. If you see that plane of linear polarization with the sky, the CMB is rotated uniformly by some angle beta, it is a sign of parity violation. This is called cosmic birefringence, because birefringence of polarization of light in crystal. So if you shoot polarized laser into sapphire, then plane of linear polarization laser will be rotated by the double refraction, so birefringent effect. It's not even in physics, you see. So we're basically thinking maybe space filled with dark matter or space filled with dark energy, which could couple the photons in the parity violating manner, will cause this effect. If that's so, if that's the correct interpretation, we discover that dark matter, dark energy violate parity. And to me, that's completely reasonable. Okay. All right. So let's do exercise. So I rotate plane of linear polarization by beta, then observed E and B. So both E and okay. So observed E and B are related to original E and B at emission times this phase factor. That's a rotation of plane of linear polarization. Then E by E at emission times cosine and B at emission times sine, and B is similar, analogous. What's important is even if you didn't have any B at emission, so let's say this is 0, you will have non-zero B, two birefringence. And if you take E times B, that's proportional to EE times sine 4 beta. Yeah? So you can do the math and you can convince yourself that the EB observed is given by tangent 4 beta times difference between observed E and observed B. If the observed E and observed B are equal, okay, so this will be 0, and you cannot probe parity violation. And luckily, we have a gift from the sky. We know that the power spectrum is much, much bigger than B mode power spectrum. And this E mode power spectrum has this so-called acoustic oscillations due to sound waves in the early universe. It has a very distinct shape. We have everything. We measure EB. We know what this EE minus BB is, and let's fit it. Beautiful fit. Chi-square is 66 for 71 degrees of freedom because we have one free parameter. Yeah. 9 sigma detection. It's 0.3 degrees. Is this due to galaxy? No. You get similarly beautiful fit regardless of the sky cut you apply. You can explain these measurements by uniform rotation of plane of linear polarization of the C and B over the sky. Now, we have the enemy, okay? So namely, what we see is a uniform rotation of plane of polarization. This can be caused by cosmological effect, cosmic birefringence. It can caused by also calibration of your instruments. So let's say you have a focal plane, you have detectors which are sensitive to certain direction in polarization. You rotate your focal plane by alpha, you can completely mimic the effect of beta, cosmological rotation. So either universe is doing rotation or you are doing rotation yourself, right? You rotate yourself and think that maybe it's the universe doing it. So basically you have this miscalibration alpha and then beta is a genuine cosmological effect. We can only measure the sum unless you have some extra information. So if you look at the literature, okay, for example, this is such a fascinating subject that we decided to look at it in a WMAP data a while ago. And it's a happy time that we never found any significant angle rotational angle. So error was large. But then 2016 Planck correlation showed 6 sigma. So now we have 9 sigma, but they have 6 sigma. Then polar bear correlation reported, but opposite sign. SPD correlation reported 15 sigma, but twice as large as Planck, and so on. Basically, they are all affected by alpha, and then you have to calibrate alpha and add that calibration uncertainty to your error budget. So WMAP was calibrated only to 1.5 degrees, quad was calibrated to half a degree, Planck 1/3 a degree, right? And these measurements don't really have calibrations. So they were stuck, right? So we cannot make progress further unless we know what the alpha is more precisely. But both WMAP and Planck left L2, and we cannot go there and fix the instruments. So we're stuck. What do we do? Then we had an idea. Because these birefringence accumulate over distance. Whereas we have this polarized emission from our galaxy that was emitted only 10,000 light years away, 14 billion years ago. Yeah? So the distance traveled by light of this polarized galactic emission is much, much shorter than the distance traveled by CMB photons. We can completely ignore birefringence for this foreground emission. So we can use a polarized foreground as a calibrator and then determine alpha. And this actually worked quite well. And we were able to recalibrate instruments of WMAP and Planck. Planck has two instruments, low frequency instrument, LFI, high frequency instrument, HFI. And to my satisfaction, these are recalibrated results. These are posterior distribution of recalibrated angles. They are all within the calibration precision. So I said that WMAP was calibrated to precision 1.5 degrees. And indeed, all of the angles of WMAP recalibrated are within 1.5 degrees. And Planck, each of this HFI, LFI detector was calibrated to 1 degree precision. And indeed, all of these red and green fall within 1 degrees. Everything is fine. And then they're also random because each instrument will have miscalibration that's independent of each other. So we can use this to remeasure birefringence. Now we have 9 sigma signal, which you decompose into miscalibration alpha, that's red, and birefringence beta, that's blue, and green is the best fit, taking into account both. So our conclusion is it is 9 sigma signal. But because we decompose this signal into 2 components, alpha and beta, the significance for beta is now 3.6 sigma, and its chi-square is beautiful, okay? Is this galaxy? No, you get the same answer even if you mask galaxy. But if you do mask galaxy, because we rely on galaxy for recalibration, uncertainty on beta, uncertainty on alpha inflates, and therefore uncertainty in beta inflates also. So we have a little bit more than 2 sigma signal, not 3.6 sigma, but it's decent, statistical significance, even if you mask a lot of sky. What is it? If you remember your electromagnetism course, you know that original polarization can be rotated by magnetic field, Faraday rotation. Why not have that? Then I remind you that Faraday rotation depends on photons' energy. So beta of Faraday rotation is proportional to 1 over photon frequency squared. We can test that. Then we fit our data to beta going like frequency to the nth power, and it will be -2 for Faraday rotation. It's not -2. It's actually small, and it's consistent with 0. It's not Faraday rotation. What is it? Can it be due to non-cosmological effects that we didn't take into account? And that's entirely possible. All I can say is we looked at all known instrumental effects, all known foreground effects, and we couldn't explain this signal, okay? It doesn't mean that it cannot be due to non-cosmological signal. It just means that we need independent measurements from independent experiments done by independent people. So not WMAP or Planck, but things like Simon's Observatory, Atacama Cosmology Telescope, BICEP, and so on, okay? And they are taking data. So they will soon tell us what they are finding. Okay. But if it is cosmology, okay, then we can explain this beautifully by dark matter or dark energy. So let's say the sky is a neutral scalar field responsible for dark energy or dark matter. Now, if it is dark energy, what is it? What does that mean? It means it's a dynamical scalar field. It's not cosmological constant. That's a very interesting thing to know, right? If it is dark matter, we know that at least a fraction of dark matter violates parity symmetry. And who will be surprised, no? That the dark matter violates parity symmetry? After all, weak interaction violates parity, and dark matter is kind of weakly interacting, right? So I think that would be nice to know. So let me summarize. I hope I convinced you that parity violation is a new topic in cosmology. It's exciting. It may really answer the questions like what is dark energy, what is dark matter, and we have 3.6 sigma hint for cosmic barrier fringes. Space may be filled with parity violating dark matter, dark energy fields, and we're waiting for confirmation or rejection from the other experiments. And you can also look at other things like galaxy shapes, gravitational waves, galaxy 4-point functions. And I think we just have to dig into the data and test parity that we haven't tested before. So I stop here. Thank you very much.
Great. Thank you very much for a fantastic talk. So we have time for questions and discussion. So raise your hands in Zoom, or Joe and Martian can help me in the other rooms. And please go ahead and ask your questions. Maybe I can start then a little bit here. So let me try and get my head around all these things. So first, the actual signal and the reliability and the galaxy foreground. If there was some dominant galaxy foreground, even at high latitudes and so on, can you remind me why you think you could exclude that?
Yeah, because basically the shape of the this signal, right? So first of all, this signal exists regardless of the sky cut, right? So if it's galactic high latitude, foreground is doing it, or also it's so bright on the in the middle plane. If galaxy is doing it, then it should depend on how much galaxy you mask, right? But second thing is really to answer your question, what about galaxy and high galactic latitudes? This has this very distinct acoustic oscillation. I mean, it's not obvious when you look at the raw data, yeah? But if you fit to this E-mode power spectrum you measure, it's a beautiful fit. And no galaxy acoustic oscillation. Really quite compelling, right? That this rotation of linear polarization of the CMB is a good explanation.
No, it looks great. Yeah. Gina.
Yeah, hi. So great talk. So two questions. One to follow up on Jonathan's, but what if we had a situation where the E mode of the CMB is not very much affected by the foreground and the B mode is more affected because it's lower, right? So you could still get the acoustic oscillations in the signal that you're showing from the E, but then wouldn't your B, like, could your B be more affected by the foregrounds at high latitude? That's my sort of thought.
It could be, yes. But if E is CMB and B is foreground, there wouldn't be any EB correlation. Like CMB and galaxy wouldn't be correlated. It's right. EB correlation. It's a cross correlation between E and B. So if E and B came from different physics, there wouldn't be any correlation.
Okay, I see. And the actual question I wanted to ask is, okay, so you said in the beginning that you need to average over the whole sky to get zero if there's no parity violation. But like BICEP and the other experiments are only looking at a small patch. So how can they probe that?
Yeah, so that's an excellent point. So if you just detect EB in 1% of the sky, that's not the the whole story. You have to repeat this measurement at different locations. So indeed, if 1% of the sky bicep patch, 500 square degrees, shows some EB. Other patches, same size, 1%. If they have negative, positive, and if you average over them, it's 0. It's not parity violation. It's an interesting effect. You have spatially dependent EB, but that's not parity violation. So you really need to have full sky average to say something about parity.
But does that mean then these experiments are not going to be that useful for this? You need a space mission or something?
So this will be very useful to at least see whether it is due to systematics or genuine cosmological effect. If we get the same answer from satellite and bicep in the same patch,
yeah,
that particular patch of EB, then that's really compelling, right? So because it's a different experiment, different systematics. And you can calibrate your instrument quite well if it's a ground-based experiment. It's much easier to calibrate ground-based, not rather than space. So that's really super important. And in Bicep 3 collaboration recently published a paper on their calibration. And their calibration uncertainty they achieved on the ground is 0.3 degrees. It's almost there. So if they improve their calibration by factor of 3, and they can tell us whether they see the same signal or not. And that'll be really awesome.
Great. Any other questions online?
There's a chat. I think Naoki asking something.
Yeah. Well, I can read. I don't know, is Naoki still here? But let's see. When we on the Earth see the CMB as left-handed, does an alien on another planet in a distant galaxy or even a separate universe see their CMB as right-handed? So does it depend on our spatial location? Just a fluctuation, I guess, from where we are.
Yeah, excellent. Yeah, that's a very nice thing. So let me explain. I think I can answer this. So let's look at the multiverse, okay? What's happening in this particular model, okay, here, is that our universe has a homogeneous chi. Rolls in some direction. And this parity variation is basically determined by the derivative of chi dot. And because of inflation, our universe has a homogeneous chi that goes in some direction. And this will give you either right-handed or left-handed, okay? But if you go to another universe, its own inflation, then their chi dot can have opposite sign. So they will indeed find a direction, right? So if you average over all multiverses, you get 0.
Well, why do we need to go to different universes? Can we first, within our own universe, if we go to different places, what do you?
That's right. So let me explain. So this term here, particular term here, violate parity. In fact, this FF dual is a pseudo-scalar. Chi is a pseudo-scalar also, let's say. This whole thing doesn't violate parity. So therefore, if you average over all possible possibilities in the universe, it should not generate a parity violation. But in our universe, that this chi takes on vacuum expectation value that rolls in one particular direction. Then parity is spontaneously violated. Our universe. It's more like a spontaneous violation rather than explicit violation parity in the Lagrangian level. So this explains why we ever get parity violation from term like this. And this explains why our universe has one particular value of parity violation, the other universe doesn't have. Right? Now, what about within our universe? Chi, homogeneous component, right? So we have homogeneous dark matter. No matter where you go in our universe, it should give you the same parity violation. So if you go to other planets, our observable universe, they will see the same beta, 0.3 degrees. This will tell you, this will give you to communicate what we mean by right and what we mean by left. Right? So you go to the alien, you have email exchange to alien, and alien will say, what do you mean by right? What do you mean by left? And you ask them to measure barrier fringes. And they will know what we mean by right. Right? That's the direction of plane linear polarization rotation. So in our universe, we have a uniform reference to say what is right, what is left.
But we had to use the
Yeah.
beta decay as well, couldn't we? Or
Yes, yes, yeah. You can also certainly ask them to do Wu experiment, right?
no.
Then let them figure out the helicity of neutrinos.
Yeah. Okay.
Or discover that. Yeah.
I still may have to get my head around your answer there, but let's move on to other. Kathy, do you want to verbalize your question, please?
Yes, thank you. Thank you so much for this fascinating talk. I wanted to ask you more about Faraday rotation. Of course, I don't think that it is causing that signal that you detect at the few sigma, but it could be, couldn't it be a systematic uncertainty that needs to be quantified in a proper way? Because Faraday rotation will vary from place to place on the sky. So
Yes.
it cannot just be subtracted globally, right?
Yes, that's correct. Yeah, that's an excellent point. And in fact, I talked only about homogeneous component, but there's a whole another program the researchers are doing that is to look for anisotropic rotation. And Faraday rotation is a very important topic. And if we wanted to constrain, for example, primordial magnetic fields, they are inhomogeneous. And this is a super powerful way to constrain primordial magnetic fields. And also, if it is a scalar field, right? Scalar field has quantum fluctuations. This should also give you inhomogeneous polarization angles over the sky, even if you have homogeneous component. That also gives you some ideas that once it's found, that will give you some idea about what this chi is. So far, no evidence for spatially inhomogeneous polarization angles, but that's simply due to lack of sensitivity. All the future measurements, CMB experiments, they're all looking into both homogeneous and inhomogeneous component of rotation. And that needs to be taken into account. I mean, if it's found, yes, I mean, this will add to the uncertainties. And hopefully, right, luckily, we have this, so we can do basically multi-component fit. We allow for frequency-independent component and frequency-dependent component and do simultaneous fits. In this way, you can account for properly the noise contributions from inhomogeneous components.
Right. And the Faraday effect would be related to the large-scale structure,
yes.
I would think, right?
Yes, yeah.
Yeah. Thank you very much.
Yeah.
Great. I think Devesh is next.
Yeah, hi, Professor Komatsu. I have a very naive question, really. Let's say if we find this signal of this primordial gravitational waves at cosmic inflation time, if this parity violation is true, if I may ask, what would we expect? I mean, how would this
very
signal?
Good. Yeah. So this is an important question. Okay, what is the origin of this signal we are seeing? And let me tell you that if you have parity violating primordial gravitational waves, right? Chiral gravitational wave. They will indeed give you EB power spectrum, but their shape does not look at all like this sound wave E mode. It will look more like B mode gravitational wave, right? So we can easily distinguish what we see in inflationary components, right? So what I can say is we cannot explain what we see here by primordial gravitational wave. Yeah. But it remains to be seen, no? In the future, when we do see B mode polarization from gravitational wave, then the question is, can we see EB of gravitational wave on top of the fringency effect that we see? Yeah.
Great. We have about 5 minutes left. I'd like to extend it to a little bit, well, perhaps more speculative things. there are other asymmetries in the universe, like matter, antimatter.
Yes.
And can you speak a little bit about if you foresee any connections to some of these things?
Yes. So, for example, this EV power spectrum tells you only about parity. Doesn't tell you anything about charge. Tell you anything about time, right? So CP or CPT. Matter asymmetry, matter antimatter asymmetry requires CP violation. These measurements a priori don't really tell you anything about that. But once you fold your model in like this, then you can start talking about CP and CPT. For example, this term doesn't necessarily violate CPT, but you can rewrite this term in such a way that it violates CPT. Okay, can explain our measurements beautifully well. So there's another whole community testing Lorentz invariance and CPT invariance of physics. So they are very excited about these measurements, right? Because it has implications for CPT violation. That's huge. So then, yes, I mean, for example, matter-antimatter symmetry, people speculate that if you have this kind of term during inflation, now it's coming to Devesh's question about primordial gravitation waves, primordial parity violation, they can produce baryon asymmetry. Yes, they can certainly, term like this can give you baryon, anti-baryon asymmetry, in fact. Could be related to EV correlation of primordial gravitational wave that will look like this. So if in future, so not this effect, right, that we are talking about, this is a later time effect. This is a rotation of linear polarization after recombination. But if we do see in the future EV from this gravitational wave, this has a direct implication for matter baryon, the matter anti-baryon symmetry. Yeah.
So, but then this birefringence that's happening later, I'm trying to understand what exactly it implies. And could it
that's
be
right. So that it could be dark matter, dark energy. Dark energy is later time effect. Right? So you have a dark energy that's scalar field which is coupled to photons in parity violating manner. So we know, first of all, dark energy is not a cosmological constant. I think that's pretty big. And on top of that, we know that the dark energy actually couples to photons. And that's super cool, no? So that will be the implication. And I think this has lots of implications for quantum gravity theories that will try to explain cosmological constant using vacuum fluctuations, for example. So it's it has a number of implications for that.
What if the universe had some net rotation? Is that a silly question?
No, it's not silly. I mean, people let me repeat my slogan: don't take it for granted. Anything rotation has to be tested, and people have tested it. For example, one of the things that people did right after Kobe was to look at evidence for rotation, because we have a rotation. There's a particular blue shift and red shift that you can observe in CMB anisotropy, and didn't find anything. Therefore, you can put upper bound on rotation that's 10 to minus 5, right? Same order of magnitude as delta V over T. People are still doing it, and they are improving on the limits on rotation now. So there's a group in Imperial College London. They're studying topology and also rotation, shear, and all these interesting effects, global effects. We should keep looking at it. I mean, similarly, I have also looked at spatial homogeneity and spatial isotropy. These are fundamental assumptions, but we have to keep testing these assumptions. So I mean, we keep testing them.
Great.
Yeah.
Very good then. Well, given that what you mentioned about the limited field of view of the ground-based experiments, when do you think we'll have a definitive answer on this?
Yes. So Simon's observatory, actually Atacama Cosmology Telescope, they have 14,000 square degrees. They cover a third of the sky. That's pretty good, right? So their measurements will be announced either end of this year or early next year. So I'm really anxiously waiting for it. but they don't have very good calibration. So their result wouldn't be definitive. Simon's observatory has calibrator built in, and they also observe a big chunk of sky. So I think Simon's will be pretty close to definitive. And then that's, I think, they started observing already. So 3 to 4 years. And my expectation is if they don't find anything, we'll hear the result very soon. If they do find something, take a while before we hear anything from them because they wanted to be super careful, right?
Right.
Yeah. But I think we're talking about less than 5 years from now.
Great.
Is Lightbird too low resolution to test this?
Lightbird is a longer time scale. So current launch date is 2032. So that will be already end of Simon's. That's why I didn't mention it. But of course, right, Simon's confirm Lightbird. And we have to do this full sky. Yeah. Then we can do even more physics with it. With Lightbird, we can actually test, for example, I mean, didn't have time to talk about it, but to tell whether it's dark matter or dark energy, difference between dark matter and dark energy shows up on the largest angular scales, actually. So this recombination, reionization bump, so to speak, this has to be measured in EB. This measurement is limited to only down to L of 50. This is L less than 10. And to measure this, you need Lightbird. Simon's observatory cannot do it. So if Simon's observatory confirms this, the question is, what happens here? That requires Lightbird. 10 to 15 years. Yep.
Great. We're at the hour almost, so I think let's thank Ichiro again for a fantastic talk and inspiring discussion.
Thank you. Thank you for the invitation. Bye.